warahmatullahi wabarakatuh for the introduction for our system protection. Power distribution system is essential for delivering electricity from the power plant to homes, business, and the industry through components like transformers, switchgear, and distribution lines and substation. Effective planning and design must prioritize efficiency, adaptability, and resilience to meet changing energy demands. Power analysis is critical in maintaining system reliability, as issues like short circuit or equipment failure can disrupt the service. Engineers use fault analysis to minimize risk, improve stability, and ensure the continuous power delivery with protection devices like circuit breaker and diffusers, helping to safeguard the equipment and users. This project provided hands-on experiments with the practical applications of distribution system and fault analysis, reinforcing the importance of safety and reliability of real-world settings and helping us develop better solutions for future energy challenges.
Bismillahirrahmanirrahim. Assalamualaikum and good evening to Dr. Friends. My name is Muhammad Zudi bin Azlan. My method number is DE2052 and today I will present about the objective project, which is we have 6 objective project before we start the project. So the first objective project is which is the power distribution system analysis. So understand to the structure of the key component of the power distribution system, including the transformer, switchgear, distribution line, and substation, and assess how the components contribute the reliable, safe, and efficient power delivery. Second objective project, which is the fault current and fault analysis. Classify and analyze common fault such as a short circuit, ground fault, and open circuit fault. Examines the cause and impact of the throw fault on the system performance and safety. Simulate fault scenario to evaluate how the system respond and identify protection needed.
Next, we have 3 relevance of fault protection scheme. Firstly is minimizing system downtime. It is very crucial for efficiency. Fault protection schemes rapidly detect and isolate faults, so they can ensuring that unaffected areas remain operational. Next, we have system reliability and stability. So this system is a power system and very essential for our system. Fault protection schemes prevent the cascading failures and help maintain voltage stability. Last but not least, we have adaptability and economic benefits. From economic benefits, we can adaptable to system growth. Therefore, we can assuring the safety even as demands increase. So we can also save the cost.
Okay, next for literature review. So basically, power distribution system (PDS) will deliver electricity from transmission network to use through components like substation, transformer, and distribution line. So they are aimed to provide reliable power, reduce energy loss, and manage power. So in era of modern energy, the modern advancements such as smart grid will use sensor and advanced control to optimize power flow, detect fault quickly management outage, which is common fault include as short circuit, ground fault, and open circuit, which are managed use protection devices like relay, fuse, and circuit breaker.
For the importance of fault protection scheme, there are 7, which is ensure safety, protect personnel and equipment from hazard like shock, fire, and explosion, enhance reliability, maintain system stability by quickly isolating fault, reduce the downtime, isolate faulty section while keeping the rest operational, then prevent damage, protect critical equipment from the overcurrent, overvoltage, and overheating, improve efficiency, maintains optimal system performance and power quality, and then save the costs that such as lower repair, replacement, and outage expenses. And the last one is ensure compliance with safety standard and regulatory requirement.
Assalamualaikum warahmatullahi wabarakatuh and good evening. So today I will explain about the methodology of our project. So we'll start with the load flow of study. The load flow of study is the next essential step in the analysis, which comes after choosing a suitable power system model. One essential tool in power system engineering is a load flow assessment, sometimes referred to as a power flow analysis. In these studies, the complete network of buses, transmission lines, generators, and loads will have their electrical power distributed simulated. One of the major objectives of the load flow study is the estimation of the maximum current flowing in each line within the power system. These values of maximum load current are important parameters because they define the normal operating limits of all components within the system. It will hence allows engineers to maintain that the system infrastructure is neither overload nor underutilization, but a critical balance between efficiency and safety. The result of the load flow study then form the basis for the design and calibration of protection system, especially overcurrent protection. Load setting must be cautiously selected in such a way that discrimination between normal operating and fault condition it become to reducing to a minimum the possibility of spurious trips, but ensuring repeat fault occurrence if required. Next, I will present about the fault simulation study. Fault simulation study is the second most important task in the analysis of the load flow study. This step is a vital importance for the determination of the behavior of the power system under abnormal operating condition. Estimation of this scenario by engineers enables them to predict system response and design effective protection mechanisms that will protect the equipment for continuous operation. The different fault types will be brought into system in various simulations at strategic locations within our system. It provides analysis of maximum fault current peak and flow in condition for such fault that may represent the highest current flowing because of the different system dependence at fault endurance. The following fault to be analyzed are single phase to ground, line to line, double phase to ground, and three phase to ground from this simulation. It is impossible to identify the peak and the minimum value of the fault current. The fault simulation study also provide insight into the system resilience and possible impact on the power quality and stability. Worst case scenario can be simulated to which point of the network can be found on which data disciplining can be developed by the engineers. It will also serve as testing ground for the protection scheme to be applied on the system for its accuracy and reliability. The result of this step are prime important in setting the overcurrent relay and in making the system operate within the realm of safety under variable fault conditions. Generally, a fault simulation study can be regarded as a fundamental part of protection design in our systems and contribute to its stability, reliability, and overall performance. Next, I will explain about the overcurrent protection device. The overcurrent protection system is a significant area with the domain of the power system for its safety and reliability in the operation. This hugely relies on data obtained from load flow analysis and fault simulation. The important information with regards to the behavior that the system might operate is derived from it. The key objective is the selection of appropriate setting for each overcurrent relay such that their operation may take place under abnormal or faulty condition. Overcurrent relay can play a major role in the detection and location of fault section in the power system. Accurately settings such as pickup current, time dial, and characteristic curve have to be chosen in an attempt at some compromise between sensitivity and selectivity. Settings that are too insensitive, on the other hand, will fail to respond promptly enough in case an actual fault takes place, possibly involving equipment and safety. In a nutshell, overcurrent protection design is realized based on load flow and fault simulation data for correct and reliable operation of relay by carefully choosing the setting of relay and good coordination in order to obtain selective protection. The design improves system reliability is isolated section where the fault has occurred in order to minimize disruption in the healthy parts of them, making it resilient and dependable.
So this is diagram of our flowchart. So we start from the oval shape, which is start. Next, we need to find the input data and designing the circuits. So after that, we proceed with the declaration of load flow and analysis and load current of the circuit. If the overcurrent occurred, so we proceed to use the power protections. If the overcurrent doesn't occur, so we declare again the load flow analysis and load current of the circuit. So after that, we give the analysis about the result that we get. So last but not least is the ending process. From the left, we can see the diagram of the circuit line to ground when the fault current occurs. The main point of this diagram is to show the line to ground fault at bus 11, which creates the direct short circuit for all three phases to the ground. Therefore, this can lead to high fault currents, which can give us the harmful for electrical equipments and disrupt our circuit system operations. So, we need to improvise the grounding system, which can help manage fault current while maintaining the sensitivity for protective relays. Besides, from the left, we can see the diagram of the circuit line to ground when have a system protections. The main point of this diagram is to show the circuit breaker at bus 11 in conjunction with overcurrent relays and a grounding system. This can protect the generator and transmission line from the high fault currents. High fault currents is occur during events like a three-phase line to ground fault. The highlight this circuit is about the breaker's role in isolating the generator and the grounding system functions. So they can limit the fault current to minimize the damage and also ensure the effective operations of protective device.
Next, I will explain about the circuit line to line fault current. The circuit illustrates a three-phase electrical system where a simulated three-phase fault has been inserted a line-to-line current fault using a MATLAB software. Bus 11 is a central node used to distribute the power across three-phase source, loads, bus, and a fault location. It has the provision to simulate the condition of power flow and fault prevailing in the system. Three-phase load block represent a connected load which has the resistive and inductive characteristic with real-world behavior of the loads. It permits the study of the response of a load to voltage disturbance and fault current. In a three-phase, all three-phase ABC come into contact or can be called as a short circuit. This type of fault creates the worst case Fault condition. Lush fault condition. Lush fault current flows in fault because of low impedance at the point of the fault. The circuit include a bus, which is bus 11, is used as a central connection point, a three-phase load with resistive and inductive characteristic and fault detection points. A protection system must be implemented in order to protect the system. Lastly, I will present the circuit line-to-line with its system protection. So the circuit simulates a line-to-line fault with protection system and its related component in a three-phase electrical system that have been modeled in MATLAB. A balanced three-phase supply is connected to the rest of the network is provided by the system three-phase source block. To guarantee system stability and appropriate fault current, the source is grounded. Bus 11, which serves as the main hub for the power distribution, is connected to the source's output. In order to simulate the combination of the resistive and inductive loads, the circuits additionally incorporate a three-phase load block connected downstream. This is one of the most frequent faults that resulting in overheating and damage to the equipment, and voltage instability in the faulty section is not removed as quickly as possible. Against this type of fault, the protection can be affected by combining some relays. Some overcurrent relays will constantly monitor the line current and will trip on excessively higher magnitudes of current flow. The diffraction relay will estimate the incoming and outgoing current in the lines and detect any discrepancy caused by the fault. Circuit breaker that will be connected to the bus 11 shall isolate the faulty section upon acting by the relay. Current transformer are very important for correct current monitoring and as input to relays. Besides grounding, provide safety for the safe dissipation of fault current. This protection measure will prevent system damage, maintain stability and reduce downtime in cause of fault.
Assalamualaikum dan salam sejahtera. Nama saya Muhammad Syudi bin Azlan, nombor matrik DE 22052 dan hari ini saya akan membentangkan sikit tentang result yang diperolehi daripada keluarga kami. So untuk permulaannya kita orang menggunakan IEE 14 circuit, which is kalau tengok sebenarnya dia besar, tapi kita akan ambil satu contoh yang simple untuk membuktikan yang protection tu function apabila berlakunya ada sebarang fault current. So contoh kita buat kita gunakan three-phase fault untuk fault current line to line. So ini merupakan circuit sekiranya tak ada protection. Okey, untuk protection kita orang gunakan three-phase program voltage source. Ini merupakan protection bagi current bagi sekiranya ada fault. Okey, sekarang saya buat demo sikit. Ini merupakan waveform di mana three-phase yang ada fault current. Sebagai contoh dekat sini, saya zoom sikit. Sekejap saya zoom. Sini nampak. So ni ada fault current kat sini, kat bahagian merah dengan biru ni, red and blue. So disebabkan itu kita tambah protection dalam three-phase fault ni supaya tiada lagi berlaku. Okey, kita run. Okey, sekarang kita tengok. So dah tiada lagi berlakunya sekarang fault current sebab kita tambah protection. So ia juga kalau boleh tengok kat sini kita setting juga dia punya parameter. Ini kita guna 50Hz, phase negatif 120 dan amplitude 0.91. Untuk ni pula kita guna switching frekuensi 1/60 dan 5/60. Ini merupakan contoh bagi line to line current. Merupakan simulation bagi three-phase line to ground, which is kalau kita nampak kat sini kita ada A as a ni ABC ni red, yellow, blue lah, three phase. So kita gunakan C as a ground, A as a dia punya ni lah three phase punya. Kalau tengok dia dah berubah sikit. Tadi kita tengok dia punya degree phase degree dia negatif 120. Untuk yang kali ni untuk line to ground ni dia punya degree 120. Frekuensi sama dan dia punya amplitude sama. Dan ini pun sedikit lain, dia punya dia punya switching sama, cuma dia punya capacity dia sedikit lain. So kita run sebagai contoh. Kalau kita tengok kat sini, kita tengok kat bus. Okey, akan ada berlakunya fault current juga dekat sini. Okey, dekat magnet ke ni juga 16 juga, sama juga 0.016. So kita akan letak protection. Kita akan run. Dan akan sama juga bus dekat sini tadi kan. Kita tengok balik minit ke-16 kan, sekarang dah okey nampak. So kat sini membuktikan yang pentingnya ada protection. Sekiranya ada berlaku apa-apa fault current kat semua bus, sini membuktikan bahawa protection sangat penting. Sekiranya ada apa-apa berlaku fault current, dia akan stabilkan balik current. Itu sahaja dari saya. Sekian, terima kasih.
Assalamualaikum warahmatullahi wabarakatuh. I'm Ahmad Baihaqi bin Suzaki and my matric number is AE20024. Next, moving to the discussion part. The first one is the line-to-line fault current analysis, where the fault behavior shows that line-to-line faults will result in sudden surge of high oscillatory currents caused by the direct connections between two phases. These faults will lead to the equipment damage, overheating, and potential instability in the system due to the irregularity and high amplitude of the fault currents. The protection mechanism effectiveness for this line-to-line fault current will show the protection this system detects and isolates faults which significantly reduce the fault currents and restore the system stability. This will prompt the fault isolation that will prevent cascading failures and minimize the disruptions across the network. The second one is the line-to-ground fault current analysis, in which the fault behavior shows the line-to-ground faults will cause steep increase in current that leads to system imbalance and excessive neutral currents. Such faults will disrupt the normal operation of the system, raising safety concerns and increase the risk of equipment failure. The protection mechanism effectiveness for this line-to-ground fault current shows the protection system will effectively isolate fault traces, suppressing fault currents and restore the system's balance. Quick response will minimize the thermal stress on equipment and ensure the reliability of the remaining network. Next, for the proposed protection system with justification, the first one is the overcurrent protection for fault detection. The implementation of this overcurrent protection involves the overcurrent relays that are strategically placed within the power distribution system to detect abnormal current conditions and trip the circuit when faults are detected. The justification for this overcurrent protection from the Electricity Supply Act 1990, Act 447 mandates the use of appropriate protection to ensure safe electrical installations in Malaysia. The second one is MSIEC 60364-4-443 emphasize the protection requirement against overcurrent to ensure the electrical safety and system reliability in Malaysia. The second proposed protection system is the fault isolation through the circuit breakers. This implementation involves the circuit breakers that are employed to isolate faulted areas to protect equipment and minimize the impact on healthy parts of the network. The justification for this fault isolation through the circuit breakers, the first one is from the IEC 60947-2, which specifies standards for low voltage circuit breakers used for fault isolation. The second one is from the Energy Commission Guidelines. Suruhanjaya Tenaga mandates the use of certified protection device in electrical installations to prevent cascading failures. The third proposed protection system is the selective coordination of protection device. The implementation of this coordination involves the relay settings that are calibrated for precise operation to ensure only the nearest device to the fault is triggered and avoids unnecessary outage in other areas. The justification for this selective coordination, the first one is from the MSIEC 60364-5-53 that shows the details deployment for coordination of protective device to minimize the impact of faults on the entire system. The second one comes from the Electricity Regulations 1994, Malaysia, which emphasize the importance of coordination in protective systems for safe and efficient operation. The fourth proposed protection system is line-to-line and line-to-ground fault mitigation. The implementation of these two fault mitigation involve advanced protection mechanisms that will detect and respond to both line-to-line and line-to-ground faults and restore normal conditions quickly. The justification for this fault mitigation involves the Electricity Supply Act 1990 that stipulates the need for fault mitigation measures to prevent system failures and ensure the public safety. The second one is from the MSIEC 60364-4-41 that will specifies the requirements for protection against electric shock and fault currents to ensure safety compliance in Malaysia.
So the next way to add on the proposed protection system with engineer standard justification is we can add real-time monitoring and predictive analysis. For this implementation, we can integrate the monitoring system to default fault and predict system abnormalities before they can escalate. For the justification, it establishes communication standards for intelligent electronic device in smart grid system which support real-time monitoring and in Malaysia. Next, in the Malaysia Smart Grid Roadmap, it encourages adopting smart technologies for improved fault management and system efficiency. So lastly, you can add adherence to power quality standard to the solution for the proposed protection system with the engineer standard justification. So for the implementation, the protection system minimizes the voltage fluctuation and mitigates harmonic disturbance during fault. In the justification, which we have MS 2682 2018 ensures compliance with power quality standards in Malaysia to maintain voltage stability and reliability. For the MSIEC 61000 for 30 specifies testing and measurement techniques for assessing power quality in electrical system.
For the conclusion, the discussion emphasized the importance of protection system in electrical circuit to prevent line-to-line and line-to-ground fault, highlighting how harmonic disturbances can distort current waveform, potentially damaging equipment and compromising system stability. Without effective protection, fault can cause prolonged disruption. The study demonstrates how protection mechanisms, as shown in waveform figures, promptly detect and isolate fault, restoring normal system operation. This system ensures minimal downtime, maintains system balance, and enhance resilience by allowing uninfected part of the network to continue functioning. Overall, the study underscores the critical role of advanced protection technologies in safeguarding electrical system, improving reliability, and ensuring safety. That's all from me.